Hi there and welcome back to part 3 of Appendix C from Stevens' Matrices, Vectors, and 3D Math, a game programming approach with MATLAB. In this demonstration again we're going to grab a couple of files from the program or the code repository, this particular Appendix C collection of zipped files. All right. And so this is actually the third video from this specific section. The first video was plotting with the plot command. Covered these two portions of our page here. The second video did animations via a for loop, and in this last video from this Appendix C.3, we're going to do 3D plots. We'll do surfaces and we'll do curves in 3D. And so we have a couple of files for you to grab. So the first one I want you to grab is example surf, and it's in that program repository that I just referenced a second ago. So this is example surf, and once you get it open, the first thing I'd like you to do is run it. Right? Okay, so what I have are two surfaces. These are called paraboloids. Right, they're sort of a 3D version of a parabola. All right, so how did I get these graphs? Okay, so the first thing, so this is basically z is a function of x and y, if you look at it this way. And that function for this paraboloid is this function right here. This is x squared plus y squared. All right, so the height is x squared plus y squared. That's this red one here. All right. And I have to remember to use the dot squared so that MATLAB knows to square this vector x term by term and not actually multiply the vector by itself. Okay, so for both these graphs, there's two of them. There's a red and a blue one. I'm going to let x go from -4 to 4, as you can see here, and y is going to go from -5 to 5. So I create my x vectors, my x values, -4 to 4. I didn't use linspace. I used the a more traditional approach where I'm going from -4 by 0.1 to 4, and that works well because I know I'll end exactly on 4. Right? If you're doing some number like 0 to 2 pi, you certainly want to use the linspace so that you land right on 2 pi. But in this case, the colon method is perfect for building the vector. And the y vector, the collection of y values, goes from -3 to 3. But now that's just a vector of x values and a vector of y values. I want to get a whole array, right? An array of x and y values the whole way around, right? So I do that with this thing called the mesh grid. So I create these new variables, x and y, which is a mesh grid of my original x and y ranges. Right, so that gives me the whole grid, all the x's. For each y, there's, a whole bunch of x's. Right, so this is actually a very big array right here. And then my first function, my first surface, will be x. You have to go reference these, not x vec and y vec, but the x and y created from mesh grid. And so the first surface, the red one, will be x squared plus y squared. The second one will actually be a -x squared plus y squared. So it looks just like the other one, only it's flipped over the xy plane. It's going down instead of up. And I'm bumping it up by 9 so that there's some overlap. See how you can see that overlap in there? And so I'm going to plot them now that I have my two surfaces. So it's using the surf command, surf, and just like the plot command, you put in x, y, only now you include z. But remember, it's got to be the x that was created with the mesh grid function. All right? And then you can do this face call red. Right? So that plots the red surface. I'm going to do hold on so that it doesn't erase it. And I plot the blue surface. Give it a title, give it an X, Y, and Z label. That's where this X, Y, and Z came. And you can rotate that Z label so that it's horizontal, but I forget exactly how you do that right now. It's easy enough to do it. I do know that. And then this view gives you the perspective, right? It's the azimuth and the elevation of the camera, of the viewing camera. But the way I do it, the way I figure out these angles within the view directive, is I'll go over to my actual figure. Right? If you click on the figure, you'll see up here, right, there's a little rotation icon. If you click on that, you can move it around. And as I'm moving around, if you look at the lower left corner of this figure, you'll see the azimuth and elevation changing. And I just play around until I see a particular angle that makes it look good to me. And when I got to 17 and 18, I noticed that looks like the perspective I want. And then I just copy the 17 and 18 into my view command. Right? I didn't actually figure out those numbers mathematically. I just played around trial and error until it looked like I wanted it. Like if I wanted it to look like this, if you look at the azimuth and elevation down on the left, it's negative 3110. Right? I could change that to negative 3110, and now when I run it, I'll get that particular view, right? So that's how you do the surf command, and the view helps just give you the view that you'd like to see. If you ignore it completely, it'll come up with its own perspective that some algorithm in there will determine what's best, right? So it looks like that one. So if you like the default, just go with that. Otherwise, you can change it with the view command. All right, so that's how you do surfaces. Now I want you to grab this file. It's called example plot3.m. And once you grab that out of the program repository, I want you to run it. Right? And so what this plots is not only a surface very much like the previous surface, but then this is called a parametric curve. It's a 3D parametric curve. And I'll show how that's created in just a second. But notice again, once you have that rotation on, you can sort of look at the different angles on there and see how that goes. Right? You can look at it from the bottom, from the top. It's really nice. I mean, we're not actually going to do much 3D graphing until Chapter 4, but it is one of the better features of MATLAB. It has excellent 3D graphics. Okay, so how did I create this? I'm going to run it again so that it gets back to the original form. Okay, again, I start off with my clearing commands. Now I'm going to let t, that's my parameter. It's going to go from 0 to 20, and there'll be 200 points between 0 and 20. X will be the cosine t, y will be sine t. So what this does, that just basically goes around and round in a unit circle, right? And that's if you look down at the xy plane, you'll just see a circle, and that should be apparent when you do that, right? There's that circle. But z is going to go like t. So z is going to get bigger and bigger. It's going to go up to 20. So that's why you get this helix. Right, you're going around and around a circle, but t is going up, so z is going up. So you get what looks like a spring, hence the word spring. Now to plot that curve, I use the plot3 command, and that's sort of the new one here. That's what this one's demonstrating. And again, you just put in the x vector values, y vector, and z values. And then hold on. And then suppose I want to plot this green dot and this blue dot. Right, that's sort of where it started, where it stops. Well, here I'm just doing cosine 0, sine 0, 0. That's when t equals 0. Right, that's that first t value. And I know t is going up to 20, so the last t value is going to produce the point cos 20, sine 20, 20. Right? So you can plot points. When you plot a single point, you got to make sure you use this marker size and give it a big number so that it's nice and obvious where the point is. And then I just did a surface underneath it, and this was using the surf command. Again, this is a lot like the paraboloid. It's x squared plus y squared, only I have a negative 10 out in front of it, so it's really arced down. But this is exactly what we did in the last video when we did example surf. Right, but you can combine them, and you can combine them in interesting ways to make cool 3D graphs if you need to. So that's it. We have the surf command for surfaces. We have the plot3 command for 3D curves. And again, we won't get much into this until chapter 4, but it's kind of fun to play around with until then. All right, so we will see you, let's see, in Appendix C, Part 4. Bye.